In this work, from a single image captured in the wild, we recover plausible 3D spatial arrangements of humans and objects. While there has been significant progress in reconstructing humans and objects, these approaches perform these reconstructions in isolation. In this paper, we consider humans and objects jointly. PROX is a recent work that also considers humans and their environment. Using a known 3D scene, PROX recovers 3D humans in relation to that scene. To do this, PROX defines contact regions on the body to make sure that these regions are in contact with the scene, but also avoiding intersection with the environment. However, these approaches depend on existing 3D captures of the scene, which are not available in the wild. In this work, we attempt to reconstruct 3D humans and objects in the wild without 3D scans. This is challenging because there are multiple 2D explanations for a 3D scene. Consider this picture of people enjoying a park pre-COVID-19. Without understanding human-object interaction, one possible interpretation might look like this. Even though the sizes of the objects are reasonable, people shouldn't be floating in the air. The problem is that this interpretation has almost the same 2D projection as this more plausible interpretation. While for us humans, the bottom interpretation is the obvious solution, this fundamental scale ambiguity is challenging to resolve in general. For example, a small surfboard close to the camera and a larger surfboard further away project to the same 2D image. And in fact, any scale of surfboard that lies between these two camera arrays has the same 2D projection. To reduce the space of plausible arrangements, we can exploit human-object interaction as well as common sense reasoning about the size of objects. For instance, surfboards are unlikely to be extremely large or extremely small. However, to do this, the coordinate system must have metric units, whereas 3D reconstructions in general are estimated in local coordinate systems that have arbitrary units. The SMPL mesh, on the other hand, is endowed with metric coordinates, and has a prior over human shape that captures size so that people on average are around 1.7 meters tall. By placing humans and objects into the same global coordinate system, we equip objects with the same metric as humans, essentially using the human as a ruler. We denote the per instance scalar, converting between the object's arbitrary units to metric units as the intrinsic scale. To put everything together, we propose an optimization-based approach that reasons about human-object interaction. Given an image, we extract bounding boxes and use a state-of-the-art human pose estimator to predict 3D human meshes. We also predict the instance masks, which we use to fit per class exemplar meshes to the masks using a differentiable renderer. Naively placing the humans and objects into the same scene looks reasonable from the frontal viewpoint, but from top down, we can see that the composition is implausible. To resolve the inherent scale ambiguity, we present our optimization module FOSA, Perceiving Human-Object Spatial Arrangements. The optimization produces a scene configuration that is more plausible. Let's start with the 3D object estimation in detail. We use an exemplar model to represent object shape, and then we optimize for pose using a differentiable renderer. More concretely, for each image, we use point rend to predict an instance mask. Given an exemplar mesh, we use a differentiable renderer to solve for the 6th-off object rotation and translation that minimizes the silhouette reprojection error. The final pose is shown here. In order to account for the fact that objects are often included in the wild, such as the bench in this picture, we use an occlusion-aware silhouette loss. The loss tries to match the silhouette to the predicted target mask from point rend while ignoring regions occluded by other objects. The colored regions incur no loss. Here's the optimal pose found. Now, we'll move to our global reasoning module. Given independently estimated 3D humans and 3D objects, we optimize a weighted sum of loss terms with respect to the 6-soft pose and intrinsic scaling factor of each object and human. Inferring the intrinsic scales of humans using object interactions distinguishes between tall people far away and short people close by. Our loss term consists of an occlusion-aware silhouette loss, a human-object interaction loss, and a prior on human and object intrinsic scale. We also incorporate losses to encourage the correct depth ordering, as well as to avoid interpenetration. To model the human-object interaction, we take inspiration from Prox and use a parts labeling approach. We label contact regions on the human body and on each object mesh to encode common modes of interaction. For example, people usually grab tennis rackets by the handle using their hands or sit on bicycles with their bottom on the seat. In order to identify human-object interaction, we first determine if two parts interact by using 3D bounding boxes. As shown here, the handle of the tennis racket and the hand of the person are not in contact, but their 3D bounding boxes overlap. We identify this as a human-object interaction, and we impose our loss, which pulls the interacting parts closer together. Here, we visualize the improved arrangement from multiple viewpoints. To identify human-object interaction, the initial size of objects is very important. Let's revisit the surfer from before. If the surfboard is initially a reasonable size, say 2.5 meters long, then the surfboard is close enough to the person to correctly detect interaction. If we were to initialize the surfboard to be unrealistically large, the 3D bounding boxes would no longer overlap. To bootstrap our optimization process, we use an internet search to find the usual size of objects. For example, a typical bicycle is about 2 meters long. Through our holistic optimization, the intrinsic scale of the objects change. At the end of optimization, we can compute the empirical distribution of object sizes learned directly from 2D images, and we find that these values tend to be reasonable for each category. From this, we compute the empirical per category object mean size, and then we restart the process with the updated scale as a better initialization. We now show some qualitative results on the COCO dataset. Our approach can recover plausible 3D spatial arrangements from in-the-wild images across a variety of categories. Here are some more qualitative results. Since quantitative 3D data for in-the-wild images don't exist, we evaluate our method quantitatively using a forced choice evaluation procedure. We compare our results with an independent composition that uses the independently estimated 3D humans and objects that we take in as input. The scale is set using the learned empirical mean, so this composition does contain some global information. We find that our holistic global reasoning helps our approach perform better 3/4 of the time. To evaluate the effectiveness of our loss terms, we also compare our model with the ablated versions of our approach. We find that the occlusion-aware silhouette loss is important for adhering to the image evidence, and the human-object interaction loss is important for pulling together interacting components. The scale prior prevents extreme deviations from the learned mean, and the ordinal depth loss also produces a minor improvement. We found that the collision loss had a negligible and sometimes even negative effect. We attribute this to the fact that our collision loss operates only on surface collisions and is thus prone to getting stuck in local minima. Here are some more qualitative results. Please visit our project page to find the paper, code, and more results. Thank you for watching.